All right, so in the second part of this video series, I want to talk about writing vectors as symbols. Writing vectors as arrows can get difficult if you have a lot of vectors or if you aren't careful when you make your scale, and then you don't really know if the resultant that you measure is really going to be a very accurate value. So we want to learn how to add vectors algebraically. And to do that, we're going to need symbols instead of arrows. So first of all, when we write vectors, we write those symbols differently. So a vector v, it could be a velocity vector, it could be something else. When I write it, I'm going to put an arrow over the top of it. Now, some textbooks do it this way. Some textbooks make it bold. It can be difficult. You'll see in the example at the end of this video that I actually have to just kind of make my vector bold because I can't write a vector symbol over it. If I wanted to write the scalar quantity v, I'm just going to draw it, but I'm not going to put a vector over it, a vector symbol over it, an arrow over it. Sometimes this v all by itself is actually the magnitude of my vector. Often, though, I write the magnitude of my vector v as the absolute value of v. We'll probably do that at the beginning, and then as you get more comfortable understanding the difference between the magnitude of the vector and the vector itself, we'll get a little more lax and we'll just draw it as a v. So, for example, if I have a vector v0 here, and I have a vector v, I can say that the magnitude of v0 is greater than the magnitude of v because v0 is actually a longer arrow, and we talked in the last video about how the length of the arrow is related to the magnitude of the vector. Okay. So far all of the vectors that we've talked about in this class have pointed along the x-axis or the y-axis, but we know that this isn't always going to be the case. So let's talk about how we're going to deal with this. So what I have here is just a vector. I have a y-axis, x-axis, and this is going to be a vector r. And my vector r has a length or a magnitude equal to the absolute value of r, or little r. And it's going to make an angle theta with the positive x-axis. So there are three different ways that I can express this vector. Okay? So the first way that I can express this vector is just using a magnitude and direction. So I can say that the length of my vector is the absolute value of r at an angle theta with respect to the positive x axis. So I'm basically just describing what I just drew in the last picture. And remember that WRT is with respect to. So this isn't very exciting, this isn't very different, but the next couple of ways are. So I can also express my vector in terms of its x and y components. Okay, so again, I have my vector r, and it makes an angle theta with the positive x-axis. I can fill in the axes here. But if I drop a vertical down from the tip of my arrow, and then I connect the origin to that point, what have I made? Well, it's a right triangle. And you actually know a whole bunch of stuff about a right triangle, especially because the hypotenuse of that right triangle is the length or the magnitude of my vector r. So I can say that the part down here that's along the x-axis, I'm going to call that rx. That's going to be the x component of my vector. And I'm going to call the length of this vertical part here ry. and that's going to be the length of my R component. And then we know a whole bunch of stuff. So for instance, we know the Pythagorean theorem that my x component squared plus my y component squared is going to be the length of the vector squared. Or again, we may write this as just r squared. I also know some things that have to do with trig, right? So for instance, what's the sine of theta going to be equal to? Well, remember, sine is going to be opposite over hypotenuse. So this is going to be ry over r. And if what I'm really interested in is ry, I can do some cross multiplying and get that ry is equal to r sine theta. I can also talk about cosine theta. And what's cosine theta? Well, cosine theta is going to be adjacent over hypotenuse. So that's going to give me rx over r. And again, maybe what I'm interested in is trying to find Rx. And perhaps I was given the first way to express vectors, which is the length of the vector or the magnitude and an angle. So again, I can express the x component as r cosine theta. Now, some textbooks would have you memorize these. They would have you memorize that ry is always equal to r sine theta and rx is always equal to r cosine theta. I do not want you to do that because I could move theta, okay? I could, for instance, draw a vector over here. I'm going to call that vector s, and I'm going to define this angle, which is phi. Okay, and if I do that, and if you look at that, now you can see that the y component, the vertical component here, is actually going to have cosine phi in it. So don't memorize that sine always goes with the y component and cosine always goes with the x component. Figure it out, draw the triangle, draw the components every time. So in component form, which is what we're talking about, I would say that my vector r is equal to the x component, comma the y component, however you figure those out. Okay. All right, so finally, I want to talk about unit vector notation. So again, I have my vector r, it's going to make an angle theta. This is going to be my x-axis, this is going to be my y-axis. And remember those components, x and y, the rx and the ry that we had before? Well, I could kind of think about those as vectors, and I could think about moving this far in the x direction, for instance, if these were displacement vectors, and then this far in the y direction. And notice that I've got rx and ry added up tip to tail. So I've got rx plus ry added together. And remember that the resultant vector goes from the leftover tail to the leftover tip. And that's actually where I have r. Okay? So Rx is always going to be along the x-axis and Ry is always going to be along the y-axis. So it would be nice if I kind of had a shorthand way to combine that. And the way that I do that is to use something called unit vectors. Now the job of a unit vector is to indicate direction. That's all it does. And because it's a unit vector, it has a magnitude equal to 1. Okay, so remember I can multiply anything by 1 and that doesn't change anything about it. Okay, it doesn't change the length, it doesn't change the direction. So for the moment, we're only going to worry about what happens in the x and the y directions. We also have a unit vector for z, but we'll come back and talk about that later. So my unit vector is this tiny little vector here in each direction, and they have special symbols because we use them all the time. And the unit vector in the x direction is a I, and the unit vector in the y direction is a j. The unit vector in the z direction is actually a k. It's an old-fashioned engineering term. I don't really know why, but when you go to college, if you take this course again, or if you take a later physics course, these are the symbols that they're going to use. Okay? So that means that I can take my Rx vector and I can multiply, and I can express it as the magnitude of it, the length of it, and then I can tell what direction it's in by putting a unit vector. And I can do the same thing with my y component, or my ry vector. I can say that that's going to be the length of my vector times the unit vector in that direction, which is y. So then when I'm going to express my vector unit vector notations, r becomes rx plus y times, it becomes rx times I plus ry times j. And of course, Rx and Ry are going to be actual numbers. All right, so let's play around with this. Okay, we'll do an example. So a displacement vector R in the xy plane is 15 meters long and makes an angle of 30 degrees with the positive x-axis. Determine the x and y components, then express the vector in unit vector notation. So first of all, notice here that this program doesn't allow me to put a little arrow over my vector. So I had to bold it, and I'm just going to put a little arrow over there now so that you understand that it's really vector, right? And then when we solve a problem, the first thing that we do is we draw a picture. So I'm going to draw in my vector R here. It's going to make an angle of 30 degrees. The next thing that I'm going to do is make a list of my knowns. And really the only thing I know here is that the magnitude of R is 15 meters. I could say that theta was 30 degrees. So if I have to find the x and y components, let's draw them in. So remember, I'm going to drop my vertical down to the x-axis, and that's going to give me my y component, and then I'm going to connect the origin to where my y component is, and that's going to give me my x component. So again, I have a right triangle. I want to look at my sine and cosine. So I can say that cosine theta, or cosine 30, remember that's going to be adjacent over hypotenuse. So that's going to give me Rx over R. Remember, R is another way that I can express the magnitude of that vector. Or I can say that Rx is equal to cosine theta times R. So Rx is going to be cosine 30 degrees times 15 meters. And you should get out your calculator. Make sure that you're in degree mode, not radian mode, especially if you were just doing calculus. And when you do that math, you should get the same thing that I do, which is 13 meters. Notice I have 2 sig figs in my 15, 2 sig figs in my 30, so my answer has to have 2 sig figs. Okay? I can do a similar thing for my y component. I can say that sine theta, which is going to be opposite over hypotenuse, ry over r. And then I can say that ry is going to be r sine theta. My r is 15 meters, sine 30 degrees. And you too can do that math. When you do that, we get 7.5 meters. Again, I had 2 sig figs in my 15 meters, 2 sig figs in my 30 degrees, which means that I should have 2 sig figs in my answer. So here's my x component, here's my y component, and then the last part here is to express my vector in terms of unit vector notation. So my r is going to be my x component, which is 13 meters, times I. And remember, the only purpose of I is just to tell me, hey, this is the component that goes along the x-axis. That's all it's saying, okay? Plus my y component, which is 7.5 meters, times j. And j, the only purpose of j is to say, hey, this is my component that goes in the y direction. And then if I had a z component, which I don't, but I'm going to write it in anyway, I would say I have 0 times k, because k is the unit vector for the z direction, and I'm just saying, hey, I don't have a component there. You don't need to put this part. Okay, this is just extra, but I wanted to write down k somewhere. All right, so there'll be one more video that will be an example problem, and then we'll be good to go with 2- and 3-dimensional motion. Thank you.